to it. And if you do that, the sulfuric acid will, it's a dehydrating agent. It will take out the water and leave you with carbon. And the carbon rises out of the beaker and is very dramatic. But we'll find when we look at the structures that the monomers are not hydrated carbon. So they are, in fact, aldehyde or ketone derivatives of polyhydroxyl alcohols containing at least 3 carbons. So if the functional group is an aldehyde, we refer to it as an aldose, so the ose means sugar. And if we have a ketone functional group, it is a ketose. So the simplest aldose is glyceraldehyde. It has 3 carbons, and the Fischer structure, the way we use a Fischer structure is that we draw the more oxidized end on top. So the aldehyde is more oxidized than the alcohol, so we draw that on top. And we have 1 carbon with an OH group. So that carbon is chiral, you might have noticed. And because it is chiral, there are mirror image isomers or enantiomers of glyceraldehyde. So I've made a little quiz to go along with this lecture, and you can find it on Sakai. So the first question is, asks you to draw the structure of L-glyceraldehyde. So what you should do is you should pause the presentation and then draw the L-glyceraldehyde, and then you should come back and check your answer. So the OH, if the OH is pointing to the right, we call it D-glyceraldehyde. It's dextrorotatory, which means it rotates plane polarized light to the right, and the OH is on the right, which is a nice happy chemical coincidence. And L is label rotatory, which rotates plane polarized light to the left. The D sugars are naturally occurring, so Mother Nature has made that decision. So if you draw the structure of L-glyceraldehyde, you should have drawn something that looks like this. The one that's on the right. So D-glyceraldehyde and L-glyceraldehyde are mirror image isomers. We use the Fischer projection formulas rather than the R and S that you learned in organic chemistry. It's just the convention of biochemists to do that. And you can see underneath that there is that they are in fact mirror images of each other. And there's the chiral carbon right there. So L-glyceraldehyde, the OH is pointing to the left, and D-glyceraldehyde, the OH is pointing to the right. So we can have larger aldoses. So if we add more carbons, we add more OH groups because the carbons that we add have OH groups. So what happens if we add an additional carbon? Well, one of the things that we should notice is that if we have more carbons and we have more OH groups, how will we know if it's a D sugar or an L sugar? So what we do is we look at our Fischer structure and we go to the more reduced end, and the way that we draw that, it's on the bottom. And if the first chiral carbon from the more reduced end is pointing to the right, we call it a D sugar, and if the OH points to the left, it's an L sugar. So if I give you this compound right here, you should notice that there are 2 chiral carbons. There's a chiral carbon right here and another chiral carbon right here. So we have 2 chiral carbons and not just 1. More chiral carbons means we have more possibilities for stereoisomers. So we can use the formula 2 to the n, which equals the number of stereoisomers, where n is the number of chiral carbons. So how many chiral carbons are shown here? I've already told you there are 2. So that means if we do 2 to the n power, we have 4 possibilities of 4 total isomers. So here are 2 of them. So these are Aldopentoses. They are sugars with 4 total carbons. They have aldehydes as their functional groups. We call the sugar erythrose if both of the OHs are on the right, and we call this threose if the OHs are on opposite sides. And again, using the convention, this is the more reduced end, and if we go to the first chiral carbon up from the more reduced end, we see that the OH is pointing to the right. So we have D-erythrose, and this is D-threose, again, because the first chiral carbon pointing to the right is the first chiral carbon from the non-reduced end is pointing to the right. So now what you should do is you should go to your problem set that I gave you, and you should draw the structures of L-erythrose and L-threose. So what you should do is pause the presentation and draw these structures, and then come back and I will give you the answer. Well, hopefully you came up with something that looks like this. So L-erythrose has both of the OHs. It's erythrose, so it has both the OHs on the same side. And the first chiral carbon from the more reduced end is pointing to the left. So it's L-erythrose, and here is L-threose. So again, L-erythrose is the mirror image of D-erythrose, and L-threose is the mirror image of D-threose. So this compound has 2 chiral carbons, so 2 squared is 4 stereoisomers. So we have 2 Ds and 2 Ls. So we have D-erythrose, L-erythrose, D-threose, and L-threose. And then those are our 4 isomers. So we should note that D and L is a structural designation only. It's not correlated with the direction of rotation of plane polarized light. It is for glyceraldehyde, but that's the only one. In fact, I don't even know myself which ones have plane polarized light rotating to the right or to the left. You would have to look that up. So it's just the structural designation. So now let's look at the aldopentoses. So here you should answer the question, how many stereoisomers are possible with aldopentoses? So again, pause the presentation and think about it, and then come back. Well, you should have noticed that there are 3 chiral carbons, and in this diagram, all 3 of the chiral carbons are all shown here in red. And if you have 3 chiral carbons, then you have 2 to the 3rd power, which is equal to 8. So we have 8 total stereoisomers, and 4 of them are D, and 4 of them are L. And the D stereoisomers are shown here. So we have D-ribose, D-arabinose, D-xylose, and D-lysose. So in a lot of these pictures, the artist has put a box around of the sugars that are physiologically important. I'm sure you've heard of D-ribose, which you find in RNA. So you should pause the presentation and take a minute to draw the structures of L-ribose, L-arabinose, L-xylose, and L-lysose. So pause the presentation and then come back. So here they are. These are the aldopentoses. So these are L-ribose, L-arabinose, L-xylose, and L-lysose. So again, we have 8 total stereoisomers. 4 of them are D, and 4 of them are L. The D stereoisomers were shown on the last slide, and the 4 L stereoisomers are shown on this slide. And here I put a green box around the first chiral carbon from the more reduced end. And notice that all of those OHs are pointing to the left. And also, if you compare the structures of these sugars to the ones on the previous slide, you will find that they are all mirror images of their D counterparts. So now let's look at the Ketohexoses. So here is an aldopentose. So take a minute to think about how many stereoisomers are possible with the Ketohexoses. So take a minute, pause the presentation, and then come on back. Well, hopefully you notice that there are 4 chiral carbons. Here they are, 1, 2, 3, 4. So 2 to the 4th power is 16 stereoisomers. So here are 8 of them. These are all the Ds. We have D-allose, D-altrose, D-glucose, D-mannose, D-gulose, D-idose, D-galactose, and D-talose. And again, the physiologically important sugars have boxes around their names. The 4 chiral carbons are shown in pink. So these are the D-aldoses. So if you like, you can do the exercise. This would take you a while, but if you like, you could sit down and draw all of the L counterparts, all of the mirror images of these sugars. So that gives you your 16. We have 8 Ds and 8 Ls. So again, note that these are all Ds because the first chiral carbon from the more reduced end is pointing to the right on all 8 of these. So if you'd like to have some fun with ChemDraw, which I did, I went and I drew all of the mirror image isomers, and here they are. So here are all of the L and enantiomers of the D sugars shown on the previous slide. And again, just to convince you, I drew the uh, first chiral carbon from the more reduced end, pointing to the left to convince you that they were all L sugars. So here is a summary of the physiologically important aldoses. So notice at the top we have D-glyceraldehyde, and then we add another sugar to get the aldotetroses, sorry, another carbon to get the aldotetroses, another carbon to get to the aldopentoses, and then another carbon to get to the aldohexoses. And notice here that the artist has only drawn the D sugars. The L sugars are not drawn. And that's because the D sugars are the physiologically important ones. But we could draw a huge mirror plane right here and create another picture of all of their mirror images, and those would be the L enantiomers of these sugars. So I'm going to take a minute right now to discuss the different kinds of isomers. You know from organic chemistry that enantiomers are mirror image isomers, so we just have spent some time drawing structures there. Diastereomers are non-enantiomeric stereoisomers, and you're probably familiar with that because of organic chemistry too. But you probably haven't heard of epimers. Epimers differ in the configuration of only one carbon. So here are, here's an example of two enantiomers. So this is D-glucose and L-glucose, and you can see that L-glucose is the mirror image of D-glucose. So these are enantiomers or mirror image isomers. Glucose and gulose are diastereomers. I drew in red the colors of the carbons that have different configurations. So you notice that they're both D sugars, and they're they differ in configuration around two different carbons. So they're not mirror image isomers, so they are diastereomers. So the next type of enantiomers, epimers, differ in the configuration of only one carbon. So here is here are the structures of D-glucose and D-galactose, and if you look at carbon number 4, you can see that these sugars are identical with the exception of the configuration around carbon number 4. For glucose, OH points to the right, and for galactose, the OH points to the left, but otherwise they are the same. So now you should pause the presentation and answer questions 6, 7, and 8, in which you identify the type of isomers that I gave you. So here I have I've just provided a screenshot of the sugars that are on your handout. So what you should do is you should roll the tape back and look at the structures and determine the type of isomers, and then pause and come back when you figured out what kind of isomers they are. So hopefully you've determined that D-allose and D-mannose are diastereomers, D-allose and D-altrose are epimers, and D-talose and L-talose are enantiomers. So let's move on now to ketoses. So the simplest ketose is dihydroxyacetone. So the ketoses, carbon number 1 always looks like this as a CH2OH, and carbon number 2 always looks like this as a C double bond O. It's a ketone. This is called dihydroxyacetone. So the next question on your handout is, how many stereoisomers are possible with dihydroxyacetone? Well, if you think about it, there aren't any chiral carbons. So 2 to the 0 power equals 1. So dihydroxyacetone does not have any enantiomers because it has no chiral carbons. So just as we saw with the aldoses, larger ketoses are extensions of dihydroxyacetone. So we still draw it the same way. Carbon number 1 is CH2OH, carbon number 2 is C double bond O, but then we add other carbons. So we have more OH groups. So let's look at the Ketotetroses. So that's D-erythrulose. So if we look at D-erythrulose, we see that for this compound, we have only one chiral carbon. And that one chiral carbon, again, if the OH is pointing to the right, it's D, and if the OH is pointing to the left, it's L. So these are enantiomers or mirror image isomers, D-erythrulose and L-erythrulose. So two stereoisomers, 2 to the first power, one chiral carbon, one D, one L. So if we look at the ketopentoses, the next question on your sheet is how many and what types of stereoisomers are possible with the ketopentoses? So I've given you this structure here, and I didn't give you the rest of them. So you should be able to draw the structures of all of the possible stereoisomers. So the structure that I gave you is xylulose, so you should be able to figure out the other structures from just this one structure. So pause the presentation and then come on back and I'll give you the answers. So hopefully you figured out that there are 4 stereoisomers because there are 2 chiral carbons, so 2 squared is 4. And that if you're going to draw these, you'll have the xylulose, like I showed you, has OHs on the same side, but we have another sugar, another D sugar, where the OHs are on the different sides. So we have D-xylulose here and D-ribulose. The mirror image isomer of D-xylulose is L-xylulose. And the mirror image of D-ribulose is L-ribulose. So here's our total of 4 stereoisomers, 2D, 2L, and we have 4 because we have 2 chiral carbons. And again, to convince you of the naming, I've put a box around the first chiral carbon from the the more reduced end, and you can see that where the OH points to the right, it's a D sugar, and where the OH points to the left, it's an L sugar. Okay, so ketohexoses. How many and what types of stereoisomers are possible with the ketohexoses? So I will, you should stop the presentation and then come back when you've figured out the answer. Well, hopefully you figured out that there are 8 stereoisomers. They have 1, 2, 3 chiral carbons. So we have 2 to the 3rd power, 8 stereoisomers. So here are 4 of them. The 3 chiral carbons in this picture are all shown in red. So we have D-cyclose, D-fructose, D-sorbose, and D-tagatose. So again, all of these are D sugars. If you look at the more reduced end and look at the first chiral carbon, all 4 of these have the OH pointing to the right. So your next question is, you should draw the structures of the L-ketohexoses. So pause the presentation and then we'll come back. So again, the OH is pointing to the right, show you that these are the D sugars. So hopefully when you drew your sugars, you came up with something that looks like this. So we have L-cyclose, L-sorbose, L-fructose, and L-tagatose. So those are all mirror image isomers of the 4 sugars from the previous slide. And again, all 4 of them are L's because the OHs are pointing to the left. So here are ketoses. So again, here only the stereoisomers are shown. Dihydroxyacetone, it doesn't have any chiral carbons, so there's no D or L designation there. But we have D-erythrulose and L-erythrulose. We have 2 stereoisomers here, 4 here, and 8 here. So again, only the D sugars are shown because they are the ones that are physiologically important. Okay, so we're going to transition now into the formation of hemiacetals and hemiketals. So as a reminder from organic chemistry, if you take an alcohol and an aldehyde and react them in the presence of an acid catalyst, you get a hemiacetal. If you take an aldehyde and a ketone in the presence of an acid catalyst, you get a hemiketal. So this is shown in the figure down here. So here's the OH on the alcohol, and here's the aldehyde on the carbon, on this carbon right here. The interesting thing about hemiacetals is that the carbon right here, the aldehyde carbon, is obviously not chiral, but in the course of the reaction, it forms the hemiacetal, and the hemiacetal has this carbon that is. So in the course of the reaction, a carbon that was not chiral now is. And the same thing over here happens with the ketone. Again, the C double bond O here is not chiral, but this carbon here is chiral. So I wanted to remind you how this reaction occurs. If I take the alcohol right here and I have the oxygen on the alcohol can react with this carbon to form a bond. So I have a bond here between this oxygen and this carbon right here. Um, and the acid catalyst ends up bonding with this oxygen right here, and you regenerate the catalyst. So here's your hemiacetal. So in green, you can see the atoms that were originally part of the aldehyde. In yellow, you see the alcohol, and again, this carbon right here that I put a star on is chiral in the product. It was not chiral in the reactant, but it's chiral in the product. We can do the reaction with the hemiketal the same way. The only difference is we have an R group instead of a hydrogen. But again, if I form a bond between this oxygen and this carbon right here, and then these electrons form a bond with this hydrogen over here, this carbon with the star is chiral, where it was not chiral in the reactant. So I just showed you reactions where you have an alcohol and an aldehyde that are two separate molecules. But aldoses have an aldehyde and an alcohol in the same molecule. So what that means is you can have an intramolecular hemiacetal reaction. And then you form a cyclic structure. And you get a new chiral carbon because that's what happens when you do a hemiacetal reaction. So there's only one aldehyde, so that's easy. So, but how do you figure out which alcohol group reacts because there are so many of them? Well, it depends on the ring size. You might remember from organic chemistry that 5- and 6-membered rings are more stable. So you're most likely to get a 5- or a 6-membered ring. So let me show you with glucose. I drew the long chain Fischer structure here of glucose. So here's carbon number 1, that's the aldehyde. So we have 2, 3, 4, 5, and 6. And if I choose the OH on carbon number 5 out of all of the choices that I have, the next thing that I did is I redrew this, where I sort of bent this. So here's carbon number 1, 2, 3, 4, and 5. And what happens next is there will be nucleophilic attack of the OH group from the on the carbon number 5. So the bond is going to form between this oxygen right here and that carbon right there, and that's going to close the ring. So you get something that looks like this. So we've closed the ring right here, and remember this was a hydroxyl group, so that was an OH, so the H ends up over here. So you see now that this was an aldehyde. I drew this in green, but it is now a chiral carbon because it has 4 different groups attached to it. So it's chiral now, where it wasn't before. So we give this a special name. So the carbon that wasn't chiral, that is now, is called the anomeric carbon. And if you have an aldose, the anomeric carbon is always going to be carbon number 1 because that was the carbon that was the aldehyde. So the way that I carried out the nucleophilic attack, the OH ended up below the plane of the ring. So we're going to call that alpha. But suppose, I'm not so great at animations, but suppose the nucleophilic attack occurred on the opposite face of the carbonyl carbon. And again, we're going to have this oxygen is going to form a bond with that carbon, and this hydrogen over here is going to end up being bonded to that oxygen right there. So we again get a cyclic structure, but now the OH is above the plane of the ring. So this is a different molecule because this is our newly formed, our newly created anomeric carbon, carbon number 1. It used to be the aldehyde and it wasn't chiral, but now it is. So it's a completely different compound with completely different properties. So we're going to call this beta. So if the OH and the anomeric carbon, carbon number 1 if you're an aldose, is above the plane of the ring, we're going to call this, we'll call this beta. So now we have a new kind of isomer called anomers. So I drew my alpha D-glucose and my beta D-glucose next to each other, and you can see that the only difference is the configuration around the anomeric carbon. So for carbon number 1, if the OH ends up below the plane of the ring, it's alpha, and if it's above the plane of the ring, it's beta. So what that means is that you double the forms of isomers. So these compounds right here, the Aldopentoses and the Ketohexoses, can carry out these hemiacetal reactions to get either 5 or 6 membered rings. So now all of these could now have alpha and beta forms. So let's do hemiketals now. So you form a hemiketal when you react a ketone in an alcohol. And earlier I showed you a ketone in an alcohol that was a separate molecule. But a ketose has a ketone and an alcohol in the same molecule. So we're going to get intermolecular hemiketal reactions. So this is fructose. So this is what our ketoses look like. Carbon number 1 is CH2OH, and carbon number 2 is the ketone. So again, we know which one the ketone is going to be. There's only one. That's easy. But out of all the choices of OH groups, what should I choose? Well, suppose I choose this OH right here on carbon number 5. And then again, I'm going to take this and redraw it so I can show that we can get nucleophilic attack of this oxygen right here on this carbon. And when we do that, we close the ring. And remember, this was an OH group right here, so the hydrogen ends up down here. So now, for the ketoses, you can see in green, that was your old ketone group, so the C2 was not chiral. Now it is. So we have a newly formed chiral carbon that we will call the anomeric carbon. So this is alpha D fructose. So the OH is below the plane of the ring. The CH2OH is above the plane of the ring because I have no place else to put it. But the OH below the plane of the ring will use the same convention, and we'll call that alpha. So not surprisingly, if the attack occurs on the opposite face, then the OH on the newly formed carbon number 2, the anomeric carbon, ends up above the plane of the ring. So we call this beta D fructose. So here again, if we have alpha D fructose and beta D fructose, we have anomers. So again, anomers differ in configuration only about the anomeric carbon, which is the newly formed chiral carbon. So just like I showed you with glucose, if the OH is below the plane of the ring on the anomeric carbon, then it's alpha. If the OH on the anomeric carbon is above the plane of the ring, it's beta. So again, this doubles the possibilities, because these ketoses right here that can form either 5 or 6 membered rings, and remember we also have the L's too. If each of them form an alpha and a beta, we could actually have 16 total isomers. So the straight chain structures are called Fischer structures, and the cyclic structures are called Haworth structures. And you need to carry out the hemiacetal or hemiketal reaction. So I showed you a slide where I sort of bent the molecule around so you can see what happens to the OH groups. If you're just starting out doing this, it might not be that easy to do. So a long time ago, my biochemistry professor showed me a strategy that was presented in an old biochemistry book by Stumpf, and this is how I learned to do it. So you should use whichever makes you comfortable. So the way that I approach this is I carry out my my hemiacetal with my sugar still in the cyclic form. So here, if I'm going to do alpha, then this OH is going to nucleophilically attack the carbonyl. So what I do is I show here, now obviously bonds don't form bends, but I'm just showing that this oxygen is now bonded to this carbon. And then there's the hydrogen, and then there's the oxygen, and this hydrogen that was over here is now over here. So I need to take that rather strange structure and I need to convert it to a 6-membered ring. So this is how we're going to draw it. So you'll draw a hexagon and you can draw it flat. Sometimes it's drawn sort of shaded to indicate its 3-dimensionality, although it's a 6-membered ring. It doesn't really look like a flat hexagon. It looks like a chair. You know that from organic chemistry, but this is typically how these are drawn. So each one of these corners is a carbon and the oxygen is in the upper right corner. So before we go on, we have to add another item of nomenclature. So we need to distinguish whether a sugar forms a 6-membered ring or a 5-membered ring. So we have these names based on these organic compounds. So basically, if we form a 5-membered ring, we'll call it furan, and if a 6-membered ring, we'll call it pyran. So if you remember that kind of strange structure that I drew, if I'm going to convert from Fischer to Haworth, the rules are that in my Fischer structure, if the OH is pointing to the right, in the Haworth structure, I draw the OH below the plane of the ring. And the opposite is true. If the OH is to the left, I draw it above. And as we already discussed, if the OH is below the plane of the ring, it's an alpha anomer, and we draw it below, and beta is above. And if we started with a D sugar, then the CH2OH group that doesn't form part of the ring is drawn above the plane of the ring. So I used the rules on the previous slide to transition from this strange Fischer structure I drew to the Haworth structure. So here's carbon number 1. The OH is pointing to the right, and that's alpha. Here, the OH is pointing to the right, so that goes below. This is pointing to the left, that goes above. OH is pointing to the right, it goes below. And I draw the CH2OH, this carbon number 6 is not involved in the ring, so I draw it above the plane of the ring because it was a D sugar. So remember, we can form either the alpha or the beta anomer. So when I did the hemiacetal reaction to form the beta anomer, I sort of purposely drew the OH to the left rather than to the right to indicate that I had the different anomer. And that indicates the nucleophilic attack on the other side. So I use the same rules to convert my hemiacetal structure in the Fischer projection to the Haworth projection. And again, it's exactly the same except for the carbon number 1 is above the plane of the ring. So if you're very good at taking a Fischer projection, and if you can spatially take the structure and bend it around like this, then you won't have to use the Kahn and Stumpf rules that I just showed you, because then you'll just sort of naturally see what happens when you take this straight chain structure and bend it around to form the structure right here. And then if you do that, you can see that the OH will nucleophilically attack the carbon, the carbonyl right here. So, and depending on which face the attack occurs, you'll either get the OH below or above the plane of the ring. But if you're having trouble making this kind of transition, then you can use the rules that I just showed you. So what you should do now, just to test yourself, is go back to your worksheet, and question 12 asks you to draw the alpha D manopyranose. So that's how we name them. So this is mannose, and just to remind you, mannose is the C2 epimer of glucose. So the name manopyranose indicates that you are to draw the 6-membered ring. So pause the slideshow and draw the structure, and then come on back when you're finished. So there's the answer that you should get right here. So, so this is the alpha, and here, because we have a C2 epimer, that means that the OH on carbon number 2 ends up above the plane of the ring rather than below. And all of the other carbons are the same. For the cyclic fructose, I do the same kind of thing where I use the OH and do the nucleophilic attack on the carbon number 2 to form the hemiketal. And then I do the same thing. This time I'm going to draw a 5-membered ring. So I draw the ring like this, a pentagon with an oxygen on top. And now the structure will be based on furan. So if I want to draw alpha D fructofuranose, I'm going to do the same thing, where if the OH is to the left, so see this is sort of to the left of the carbon number 1 right here, sorry, to the right, the OH goes down, the carbon number 1 is not in the plane, so it goes above because I don't have any place else to put it. Carbon number 3, the OH goes up because it's to the left. Here the OH goes down because it's to the right, and this was a D sugar, so the CH2OH goes above the plane of the ring. And remember, you can have attack on either side. So if the attack occurs on the different face of the carbonyl, then the OH group appears to the left, and then you end up with the beta anomer where the OH is above the plane of the ring. And again, if you're able to look at the linear chain form right here, and then if you can in your mind bend this around and then show that this oxygen right here is going to nucleophilic attack the carbon right here, you can see you get the 5-membered ring with carbon number 1 and carbon number 6 outside of it. Now I meant to animate this, but I sort of gave away the answer. Question number 13 asks you to draw the beta D cyclofuranose. So if you're told that the D cyclose is the C3 epimer of fructose, then this is how you would draw beta D cyclofuranose. And again, if it's the C3 epimer, then the difference is the configuration around carbon number 3. So in fructose, if carbon number 3 is above the plane of the ring, in cyclofuranose, it will be below, but everything else would be the same. Again, this is beta, so I have the OH above the plane of the ring, whereas in alpha, the OH on the anomer carbon is below. So that was mainly what I wanted to talk to you about today. I did have a few other things to add that I thought might be interesting. Glucopyranose and fructofuranose are structural isomers. They all have the formula C6H12O6. The other thing is interesting is that these different sugars have different sweetnesses associated with it. So there's a scale developed where sucrose is arbitrarily given a number of 100, and sugars that are less sweet are given numbers below that, and sugars that are more sweet are given numbers above that. So just fructose by itself is actually much sweeter than glucose by itself. And high fructose corn syrup is a mixture of glucose and fructose. If you have glucose that's a little less sweet than sucrose and fructose that's a little bit more sweet, if you mix them in a certain ratio, you end up having something that's about the same sweetness as sucrose. So the way high fructose corn syrup is made is that the glucose is a digestive product of starch in the corn, and then what the food manufacturers do is they use an enzyme called glucose isomerase to convert some of the alpha D glucopyranose to alpha D fructofuranose. So you can make different mixtures, but usually the high fructose corn syrup that we find in this country is about 45% glucose and 55% fructose, which is exactly as sweet as sucrose. And it is the most valuable product derived from corn. So the next thing that you should do is there are 4 more questions on your handout. So question number 14 asks you to draw beta D tagatofuranose. Question 15 asks you to draw the Fischer structure of L-tagatose. That's actually used as an artificial sweetener in Slurpees because